the quadratic formula will determine how many solutions you have. That is the b squared minus 4ac. Okay. And see the title right here? That's called the discriminant. Okay. So right here are 4 different quadratic equations. And basically, you're going to do a few things for each of these quadratics. The first thing you're going to do is, that means you're going to do the b squared minus 4ac calculation for this. It should give you a value, and that value should be listed here. Then you're going to sketch the graph. Sketch. So you can do the graph on your calculator, and then you just give yourself an x and y axis and just sketch generally what it looks like. I don't even need a scale or anything like that, okay? And then just highlight the x-intercepts, okay, the solutions or the x-intercepts. Then tell me how many solutions you see, which will be totally dependent on the number of x-intercepts that you see, right? And then leave this 4th column blank about the type of solutions. We'll talk about that when we're done. So your job in your groups right now, okay, you can share resources, calculators, you can share information. For these 4 equations, give me a discriminant value, give me a quick sketch of the graph with the x-intercepts highlighted, and tell me how many solutions that quadratic would have, okay? Okay, so take a look at the information and how it's connected. So here are your sketches of the graphs, okay? You see in the first sketch, the graph is concave down. We should have known that because the a value is negative. That makes sense. And the graph crosses the x-axis twice, meaning it has 2 x-intercepts or 2 solutions, okay, which is what you guys marked over here. Notice that the discriminant value that goes with that is 129, okay? The next graph also crossed twice. It was concave up. Its a value is positive, so that makes sense. Okay, so sketch, it crossed twice. Notice that its discriminant is 25. Okay, so that makes sense with the quadratic formula and what we talked about. These were both positive numbers, so there were 2 solutions, which meant we would see our parabola cross the x-axis 2 times. Okay. Then in this 3rd equation, the discriminant was 0. And it hit the x-axis 1 time. Okay. Therefore, we had 1 solution. And we talked about that being the only way we could have something here that ended up just being 1 solution is if it was 0, because then when you add 0 and subtract 0, you can do the calculation, but they aren't different. They would both end up being the same. Last one, we had a negative value. Okay. The parabola did not hit the x-axis. So therefore, there were no x-intercepts or no solutions, which was fine because you guys said if we had a negative under a radical in the quadratic formula, we wouldn't be able to calculate real valued solutions. Okay? Now, that all makes sense, okay, or should be connected. Why split this one up into 2? Okay? So basically, if there's a positive number underneath the radical, we're going to get 2 solutions. But the type of solution will vary a little bit. If you're doing the quadratic formula calculation and 129 is your number underneath the radical, what are your final answers going to look like if you're just simplifying them by hand? Yeah, it's going to have a radical, right? It's going to have an irrational part to it because that number cannot be completely simplified out of the radical. There will always be some factors left underneath. So the type of solutions here, they're real. These are actually going to have real solutions, right? Except for which one? The last one, right? Because the discriminant was 0. Okay. We'll write what they are in a minute. Then what's the difference between when I get 129 and when I get 25? So like was said, if I have 129, I'm going to have numbers left underneath the radical. But what if 25 was my number underneath the radical? It's going to simplify better, right? So basically, when you have this kind of number, what am I referring to when I say this kind of number, like 25? A perfect square, okay? Compared to when you have something that is not a perfect square. So they're both positive. They're both going to give us 2 solutions, okay? But this number, when it's not a perfect square, they're going to be real, but they're going to be irrational. They still exist. I see them on the x-axis. However, am I going to look and say, look, it crosses through 3? No. It might be close to 3, but it's some like never-ending, non-repeating decimal value that I wouldn't be able to approximate. Okay? Whereas when this one is a perfect square, I'm going to see it cross twice at a nice calculatable value. Now, it still could end up being something like 1/3 or 1/6, but something that could be written as a fraction or as a decimal would end or have a repeating pattern. So here, these solutions are not only real, but they're also rational. What about when it's equal to 0? So your solutions are definitely real, because you could calculate them. Rational or irrational? Michelle? They are rational. If there's a 0 underneath the radical, is the radical going to factor into our calculation? No. Remember, the definition of rational numbers is, can you write it as a fraction? Well, if I take the radical out of the quadratic formula and I just plug something in for b and then for a, negative b over 2a is a fraction, right? So if I'm plugging in an integer number for b and an integer number for a, which our coefficients are in our quadratic, it's always just going to be whatever that fraction works out to be. So it's going to be rational, because of course it can be written like a fraction. We are taking a fraction formula with the radical no longer in it and just plugging in some numbers there. All right, so if it was negative, we said we couldn't calculate it, which means that we have no real solutions, but our solutions are what we would call complex, okay? Not as in complicated, but complex because there are these things called complex numbers that we're going to talk about tomorrow, where they take our real numbers and add the imaginary family to it, and you can write imaginary values or combinations of both, like a real piece with an imaginary piece, okay? So is everybody okay with what the discriminant tells you? It doesn't tell you the answer. It tells you how many solutions to expect and what kind of values they'll turn out to be. Okay? All right, so notice this question. Do they ask you to solve the equation? No. It just says, what is the number of real solutions? So go ahead in your groups. Danny? 0. So this turned out to be 196, and when you multiply 4 times 1 times 49, it's also 196. And here, the minus times a negative, overall, you would end up having a subtraction problem. Okay? So how many solutions do I expect? How many real solutions? 1. Okay. So 1 real solution. And then if somebody asked you a little bit further, besides just the number of real solutions, but what type of solution it is more specific than just being real, what kind of number are we going to get as our solution? A rational number. Okay? So let's look at this last problem. Okay, so lots of launching of rockets in this unit, huh? All right, so a rocket is launched from the ground with initial vertical velocity of 150 feet per second. Sounds like a physics problem. The function h equals negative 16t squared plus 150t models the height in feet of the rocket at time t in seconds. Will the rocket reach a height of 300 feet? Explain your answer. All right. So they gave me an equation that's supposed to model the path of the rocket. So I don't have to do that part, right? I don't have to come up with the equation. They're telling me the path that it follows. How am I going to go about, though, answering their question? What is the first thing you'd want to do when they ask you, will the rocket reach a height of 300 feet? Kenny? Okay, so plug 300 into the equation. It's a height, so it'll go in for h. Now, this is the problem that we would want to solve. If we solved this problem, what would we be finding? If you solved this equation, you would be solving for what variable? T. What does T represent in this problem? Time. So you would be solving for a time. A time when what happened? When it reached 300 feet. Did they ask us what time that it reached 300 feet? No. What was their question? Will it reach 300 feet? So do I really need the solution? No. Do I need to know if a solution exists? Yes. So do I want to do the entire quadratic formula calculation and find the solutions? I can if I want. You'll probably still get an answer, so that would work. But there's a faster, more efficient way, right? I just need to know, does this have solutions? So what answers that question? What we've been working on today, right? Our discriminant can tell us if this is solvable. So if I put everything on the same side together, so I can clearly see my A, B, and C values, we'll just do the discriminant calculation and see how it works out. So somebody tell me what you get when you do this. 3,300. Do we have confirmation? 3,300? Yes. So that would be the number underneath your radical. You could go and deal with that and have fun with that number. Okay? And we could go solve for the time at which the rocket hits 300 feet. But here's my question. Is the rocket going to reach 300 feet? Yes. Okay? How do I know? Because the discriminant exists, meaning when I plug this number into the quadratic formula, am I going to be able to go calculate some solutions? Yeah. Okay? So it's going to work. Okay? So my answer is yes. For the explanation part, what things would you mention? What would be your proof that this is going to happen? Sean? Good. So you would mention that you did the discriminant calculation and you got 3,300. And then you would explain to somebody what that means. What does it mean to get a discriminant calculation of 3,300? What does it mean? That there's two solutions to this problem. Okay? So I could come up with some solutions. Right? Is this okay with everybody?